So, yes. Hello, everyone. Thanks, Claire, for coming. This is Claire Boyer. She is a professor at the University of Paris-Saclay and the Institute of the University of France. And she is here today to talk to us about physics-informed neural networks and give us a statistical tour of said networks. So I'll turn things over to you, Claire. Thanks for agreeing to speak at this late hour.
Thank you, Mark, and thank you to the organizers for the kind invitation. I'm pleased to be here and to discuss about physics-informed learning and a few works that we have conducted in the recent years. So yeah, I would say the content may be a bit heavy. I hope you won't be overwhelmed, but please let me know if I need to speed up or to slow down on certain things. So what I'm going to talk about is mainly due to this work team. So in particular, Nathan Doumesh, who was a PhD student under my supervision and the supervision of Gérard Biot. Nathan was also in the, he had, sorry, because he just defended, he had an industrial PhD thesis with a French electricity company. And we got interested in physics-informed prediction problem. And then on the road, at some point, Francis Bach joined us, and you will recognize the themes that are dear to Francis at some point. Okay, so let me start with a shameless advertising about some resources that you can find online. We had the chance with Nathan to participate to a spring school in Montreal, a nice spring school. There is a humble webpage where you can find some lecture notes, some slides, but also and above all some notebooks, so you can implement directly on your computer everything that I'm going to talk about. So please, if you want to have a look, you're welcome to check this website. Okay, so I will start with the context, and the context will be for the whole talk, the hybrid modeling setting. So in the hybrid modeling setting, we are interested in some statistical model where we have an input X that is linked to some output Y through a regression function that we call f star. And of course, there is a modeling error here, so we modeled this error using some noise term. Okay. In classical prediction problem, the goal is to estimate f star, right? Because we want to be able, given x, to predict y. In the classical setting of supervised learning, usually you estimate f star using an IID training sample. So IID copies xi, yi of pairs of input and output. And what is quite particular to the case of hybrid modeling is that we have an additional prior about the regression function f star. We will assume that f star should satisfy some PDE, some differential operator that we call D, okay? And over some domain, the PDE should be closely to be satisfied. So that's why here you see close to be 0. So if the PDE is exactly satisfied, then you will have this differential operator evaluated for f star to be strictly equal to 0. But if f star is only close to be a solution to the PDE, then this is approximately 0 over the domain, okay? Okay, so then since we have those two ingredients, we may wonder why it could be a good idea to combine statistics with PDE models. so it can be a win-win, a win-win relationship. So either you're on the side of PDEs, let's say, so that are not, this is clearly not our case, but you may be on the side of PDE, you may want to solve a PDE, but your system might be incomplete. For instance, you are missing some condition on the boundary, and so you hope to use some data to help you to solve your PDE. Okay, so you need to combine the physics, so here embodied by the PDE, and the statistics, the learning part, using observation data. Now let's say that we are on the other side and we are statistician. And why would we be interested into incorporating some physics into the training and the learning procedure? Well, first, it can help for a prediction purpose to gain into interpretability of the model that is trained. And this can be helpful because if you want then to give your prediction to some applied or practitioners, they need to trust your predictions, and if they know that you use some physical models that they like, well, they might likely trust your prediction. There is also another advantage into incorporating the PDE during the training process. It's about the extrapolation concern. So what do I mean by that is that you may collect data only on a part of the domain and not everywhere on the domain where you want to estimate the function. And so to be able to extrapolate your prediction to part of the domain where you didn't have any data, the physical model may help you to do this extrapolation. Okay, so I hope that now the combination of both aspects is quite motivated. So let me start with some example. Okay, so let's say that we want to model the blood into a blood vessel in order to predict if the aneurysm that is here on the picture and here on this schematic view, in order to know if this aneurysm is going to break or not. So to do this, Arzani and co-author combine physical models and also observation to estimate the blood flow in the blood vessel. So here you have a schematic view of the blood vessel, okay, with the aneurysm here. And you want to, so let's say that the blood vessel is 2D, okay, just for the sake of simplicity. And you want to estimate this function, the blood flow F, that is here 3-dimensional, okay? To do so, you have at hand two types of information. Of course, since the blood is a fluid, you can use Navier-Stokes equation to model a fluid. Okay, so here are the Navier-Stokes equation. And you can also combine this model, this physical model, with some observation. So here you can see that we have some orange balls that represent sensors in the blood vessel where we can measure point-wise, locally, the blood flow. So here, xi will be, the x-axis will be the position in the blood vessel of the measurements, and yi will be the value of the blood flow pointwise at those locations, okay? So if we formalize mathematically this setting, for instance, well, we will be given some domain omega that we will assume to be bounded, so contained in an hyperrectangle in dimension d. Okay, so the input dimension is d, little d. And our unknown target function, the one that we want to estimate, is f star. Okay, let's say that this is a real valued function, just to be to remain simple, but this really doesn't matter. And we will be given also a differential operator, so our PDE, that f star should satisfy or approximately satisfied over omega. Okay. So with this object in mind, now the question is, how can we estimate f star? The first idea is to ignore decades of numerical analysis and to do things very, very naively. Okay, and in this to this end, you can consider three different types of sampling data. So the first type of sampling would be the regular training samples that we use in supervised learning, so the XI, YI. So in our blood vessel example, those are given by the sensors here. Locally, we measure the blood flow at some specific locations. And then we will add different other types of samplings. So in particular, the collocation points. So the collocation points here are the yellow crosses that you see a bit everywhere in the domain omega. And they are just a naive discretization of your domain. So in our work, we assume that we draw randomly those collocation points according to the uniform distribution. Okay? Of course, in practice, when you know the physics, when you know the shape of the domain, you may have better idea of discretization, but here we will do things very naively. So we just assume that we draw random collocation points over the whole domain omega. And if you have a boundary condition, so here, for instance, you know that the blood cannot cross the blood vessel, the walls, I don't know how to call it. So you know that the blood flow should be zero there. And so you can also discretize the boundary of the domain and use what we call condition points to check if pointwise the boundary condition is satisfied. Okay. So in the remainder of the talk, I will kind of forget about condition, boundary condition. We can always include them into the statistical task, but it's just for the sake of presentation that I will restrict myself to the training sample, so this part and the collocation points, okay? That is here to handle the PDE. Okay, so we can define an empirical risk function to minimize given these different types of samples. So here we have an empirical risk function made of three different terms, and actually only two terms for this talk. So the traditional one, the data fidelity term, where you will check at the input xi how your function f theta, your estimation f theta, matches the output yi that you have observed. Okay, so this is a regular empirical quadratic risk. And you will add to this a PDE term where here we check pointwise at the collocation point only if our estimator satisfies the PDE. Okay, if this quantity is large at the collocation point XLR, it means that at XLR, the PDE is not satisfied, is violated. Okay, if it's equal to 0, then it means that at XLR, the PDE is exactly satisfied. Okay, so we have NR collocation points. NR is the number of collocation points, and we introduced, of course, a hyperparameter to balance those two terms. And if you have boundary conditions, you can also add a boundary term, but I won't talk about it, where you just check it locally on the condition points if your condition function is also matched. Okay. If you minimize this empirical risk function, over the class of neural networks, meaning that here f theta is a neural network, you obtain a physics-informed neural network, a PIN, okay? So let's say that we consider the set of neural network with h hidden layers. Each layer, so here we have h is equal to 2, okay? And each layer will have the same width. So we have the same number of neurons across the hidden layers, okay? We will call theta to be the parameters of the neural network, so the weights and biases of the neural network. We will use the hyperbolic tangent to be the activation function. This is an activation function that is used in physics-informed problem because it's smooth, C infinity, so you can differentiate things and everything is fine. And so that the whole function, the whole f theta, is also smooth and you can differentiate it without any trouble, okay? In the next slides, I'm going to be interested into minimizing sequences of the empirical risk that I just introduced. So the minimizing sequences will be denoted this way. So I will call theta hat, and you see that there is a bunch of parameters. So there is NE, and E is just the number of collocation points, so of condition points, sorry. So we say that we could forget about it, okay? We have NR, the number of collocation points that we use to discretize the domain. Big D is the width of the neural network, okay? And P is just the index of the minimizing sequence, okay? So it means that when I make P run to infinity, the empirical risk of f theta hat, P, will tend to the infimum of the empirical risk over the class of neural network with h hidden layer of width t, okay? So I'm going to focus only on minimizing sequences and sorry, and this is a limitation in this work, right? Because in practice, when you train a neural network, you do not know if you have access to minimizing sequences. You use backpropagation algorithm, and you may be stuck in local minima, but we won't study where the SGD strategy that you use usually to train neural network will induce in the training procedure. Here, we will assume that we are kind of gifted and that we have access to directly to some minimizing sequence of the empirical risk, okay? So when you give an empirical risk to a statistician, the first thing that is going to check if the estimator that you will obtain by minimizing the empirical risk is consistent. What does it mean? It means that if you increase the number of samples, well, do you have your estimator that behave well and that will minimize a theoretical risk, okay? A theoretical risk that would involve an infinite number of samples. Here it's a bit peculiar because we have two types of samples, right? We have the observations, the traditional observations in number little n, and we have the collocation points, so the way to discretize the domain. And I forget about the condition part, okay? So let's just focus on the training term, the quadratic training term, and the PD term. So since we have those two kinds of sample, we will first look at a weird asymptotic regime where we only take the number of collocation points grow towards infinity, but the number of training sample will remain fixed. Why do we make this choice? Because the number of collocation points that you use to discretize, to estimate this term here, is limited by your computational resources, by your computer. You could have as many collocation points as you want, at least as many as your computer allow it, right? But for the observation point, the training sample, this is not the same story. This is usually very expensive to acquire. So in a first place, we will assume that those guys are in a limited amount, okay? And we just make NR, the number of collocation points, grows towards infinity. And in such a case, it means that we are looking at the behavior of our estimator in terms of this theoretical risk, where now we integrate over the whole domain omega this square norm of the differential operator. Okay, so here you see we take XR any points into the domain omega. So the first question that we will ask is, if I look at minimizing sequences of the empirical risk, do I have the theoretical risk of my estimator, my pin, that will converge to the infimum of the theoretical risk over the class of neural network? Okay? If it's equal here, it means that we have some risk consistency. If it's not, it means that we may have a problem of overfitting. And so, spoiler, we have a problem of overfitting. This is quite easy to construct by hand pathological minimizing sequences of neural network that will have this behavior here. So let me take this example. So let's say that we have observation xi, yi that are linked with f star. We want to estimate f star, which is some trajectory function over the segment 0, 1. Okay, so it's just one-dimensional input and one-dimensional output. And we will assume that f star is close to be a solution to this ODE. Okay, very simple ODE. But the particularity in this ODE is that you have the function that is involved, and the derivative of the function, but only derivative that are greater, that are of order greater than 1. Okay? And so what we can do is to construct explicitly minimizing sequences of the empirical risk. So the empirical risk with the training, the regular training error term plus the discretized version of the PDE error, such that the minimizing sequence is going to give you a function that look like this. Okay, so you see this is like a piecewise constant function that touches the observation exactly. So it means that we interpolate the observation at the position xi here, xi, I'm exactly equal to yi. Okay, so these are the blue points. And at the collocation points that are the cross here, well, my function is completely flat. So it means that all the derivative will vanish. And so you see that here, for this type of function, the empirical risk is equal to 0. Is equal to 0 because I interpolate my training data. So the first term is equal to 0. And on the collocation points, my differential operator is equal to 0, just because I'm flat in those areas. So, but you see, to construct such a function, you need between two different training points to jump, right? To jump, to adjust at the level of the yi that you want to interpolate next. And then by forcing those jumps, what you are doing is that you are making locally the derivative of your function explode, okay? And how can you do this with a neural network? Well, you can do this by making the weight, the norm of the weight of the neural network grow towards infinity. But remember that we are interested into minimizing sequences. So this type of neural network will you can construct a minimizing sequence of neural network that will have such a shape. And for this type of minimizing sequences, as I said, you have an empirical risk which is equal to 0, but the theoretical risk is equal to infinity just because your derivative are exploding in some specific location over the domain omega. Okay. Okay. So to prevent this pathological behavior of exploding derivative, an idea that you can have is to use a ridge regularization. So what do we mean by ridge? Is to add like an L2 penalty over the weight of the neural network. And why is it a good idea? Well, because when you have a neural network that have H hidden layer of width d, you can show that the Holder norm of your neural network, the function neural network, can be bounded by a function of the L2 norm of the weight. Okay, so if you control the growth of the weight, you will control this Holder norm, and you will prevent the derivative of f theta to explode. Okay? So we now look at ridge pins. Okay, so just a pin that is penalized during training by an additional term here, a ridge term. Is it implementable? Yes, of course. You can use any deep learning libraries that you want, and you will turn on the weight decay option during the training procedure. Okay. What we can show is that when you add this ridge penalty, then you retrieve the risk consistency that we didn't have before when the ridge regularization was not taken into account. So you can show that with the ridge penalization and the strength of the ridge penalization to scale like this with the number here of collocation points, you can forget about this one, and some exponent kappa here that is defined by the number of hidden layers that you have and the degree of the differential operator, you will have that the minimizing sequences of the empirical risk that is regularized by ridge will be risk consistent when we make the number of collocation points and R grow towards infinity. We retrieve here the infimum of the theoretical risk over the class of neural network. And if you're concerned about any approximation error, well, you can make also the dimension, the width d of your neural network grow towards infinity, and you will remove any approximation bias and retrieve the infimum over the whole class of the infinity function. Okay? So first good news, we can remove the problem of overfitting simply by this ridge penalization. And then we ask the question about the strong convergence of our pin. So here we are interested in the strong convergence of f of our pin towards f star, for instance in L2, okay, and not in terms of risk, but in terms of some functional matrix. Okay, and we also have a nasty example which is written here. So let's say that you have a bidimensional domain, omega, a square. You have some boundary condition, okay? And you look at this PDE, okay? Very simple PDE, where you differentiate with respect to the spatial component and to the time component. And we can show that for any observation xi, yi, there exists a sequence of a neural network of H hidden layer with a width 2n, where n is the number of training sample, such that the theoretical risk of our sequence is equal to 0. Yeah, so good. But the pin is always converging to 1 in L2. So what is the problem here? Well, if your goal in life is just to solve this PDE, well, you're fine because 1 is a solution of this PDE. So your neural network is converging towards a solution and then you're done. But if you are facing a problem of hybrid modeling, which means that you want to find f that is close to be a solution to this PDE, but not exactly a solution, so you expect to retrieve something from the data, well, here you see that no matter what is contained into the data, you will always converge towards 1. So we have a problem here when the physical modeling is imperfect, when we do not want to satisfy exactly the PDE, but we want to estimate a solution to the PDE plus something else. So to make things nicer here, we propose to use a Sobolev regularization. Okay. So we add another term in our empirical risk. So now we have the training, the quadratic risk, plus the discretized check of the PDE here, plus the ridge, plus you recognize here a discretized version of a Sobolev norm of f star of f theta, sorry, where we reuse the collocation points to compute this Sobolev norm. And we call theta hat sub any minimizing sequence of this doubly penalized empirical risk. Okay, and we can define also a theoretical Sobolev risk that is the previous theoretical risk, but now penalized by the true Sobolev norm of the function f. So people that have some good how do you say knee-jerk reactions in PDE can feel here that we are adding something nice for the PDE problem because we are making the risk to be coercive. Okay, so it's going to help us in terms of strong convergence of the estimator. And so that's it. That's what we can show right now. We will define the physics inconsistency matrix. So the physics inconsistency matrix is just, again, if we forget about the boundary condition and we focus only on the physics part, is just looking at, I forgot here some norms, sorry. Just to look at the integration of your PDE squared over the whole domain omega, okay? And again, we call it physics inconsistency because if this term is large, it means that the PDE is not satisfied, and if it's low, then the PDE is close to be satisfied, okay? And the nice thing that we can show about PIN that are doubly penalized by Ridge and Sobolev norms is the following. So if I assume that my target function f star belongs to some Sobolev space of regularity m plus 1, okay, and I need this regularity to be large enough, if I choose the hyperparameter here, so lambda e is for the condition part, but we forget about it, and lambda PD to scale this way, and the hyperparameter for the Sobolev part to scale this way, then we can show two different things. On the first line, you see that everywhere where I have observation, so this is mu x here, mu x is in fact the measure of my observation, okay? So if I look at the distance between my doubly penalized pin with respect to f star, and I integrate this over the whole domain where, the whole part of the domain where I have observation, then I can show that this quantity is going to be controlled by log n over square root of n, where n is the number of training samples. So this is shrinked to 0 when the number of training samples grow towards infinity. So this is good news. It means that everywhere where you have observation, if you increase the number of observation, well, you'll be closer and closer to F star, okay? And what happens everywhere else? Everywhere where you do not have observation. So it means where you are not on the support of the distribution of your input. Everywhere else, you only have the physics to help you. And what we can show is that the physics inconsistency of our doubly penalized pin is controlled by the physics inconsistency of F star plus some negligible term. So it means that the error that you are doing by modeling the physics of F star with your differential operator D is larger or is of the same in the same scale of the error that you are the physical error that you are making in your estimation of your doubly regularized pin. Okay. What does it mean? Here, I have a statistical accuracy. If I increase the number of training sample, I will converge toward F star. So that's why we call this to be the statistical accuracy. And everywhere else, well, I have a kind of physical consistency. I'm not making more error in terms of physics that I'm doing when I use the differential operator D to model the behavior of F star. So that was the conclusion of our first work, and time is running, so I need to speed up. So you see that it's kind of a big thing to train a pin, because here we are saying that to have 9 theoretical property, you need to have regularization terms and you need to discretize things. And in practice, you need a lot of data to train pins. And we said, okay, what about doing things very avoiding the discretization issue that we are actually using when we are discretizing things very naively. So that's why we wanted to apprehend the physics-informed machine learning problem as a kernel approach. So what we are going to do right now is to look at the empirical risk, but it's a bit the mother empirical risk of the previous one, where we have a data fidelity term, okay, that is penalized by a Sobolev norm, and that is also penalized by the PDE norm. But here you can see that there is no more discretization. I take the whole norm over the whole domain omega here, and here I take the true Sobolev norm at the detail, up to the detail that we are considering some periodic extension of the function f star. So it means that we are using HS pair, this space, instead of HS of omega, but it doesn't change anything about the results. You can derive the same theoretical result that I will just show to you when you are using this norm or the norm HS of HS omega. Okay. So now let's look at this empirical risk and let's stop discretizing those two things. So we keep like the true Sobolev norm and the true PDE norm. And what we manage to do is to show that this is in fact a kernel method. So it means that I can rewrite the minimizer of the empirical risk penalized by the Sobolev norm plus the PDE norm as a minimizer of an empirical risk penalized by an RKHS norm. But we need to characterize this RKHS. And once you have done this, the question that we want to ask is the PDE penalty helping you in your training procedure, and how you can leverage the whole kernel toolbox to define new tractable estimator. So in the following, I will assume that the PDE is always a linear operator of the derivatives of f. Okay. So I don't know how good you are and how you remember well the kernel methods in machine learning. There are old methods that we understand very, very well on a theoretical side. So I will be very quick on those aspects, okay? So a kernel method, you use a kernel function that is here to help you to compare two different samples xi prime. And once you have a kernel that is a symmetric positive definite function, you can show that there exists a Hilbert space that has a reproducing kernel property. So what does it mean? It means that your kernel function belongs to this RKHS, and here I write the reproducing property. So when you take the scalar product of the RKHS of any function of your RKHS against the kernel function, you reproduce f evaluated at x. Okay? Kernel methods are really extension to linear methods, to nonlinear methods. So you can have in mind that we are just lifting the problem to a higher dimensional space. So this is typically what you are doing when you use polynomial features instead of just your initial features. You are lifting the problem, your original problem, to a higher dimensional problem where you have your polynomial features. The nice thing about kernel method is that when your estimator is defined this way, so when you minimize an empirical risk penalized by an RKHS norm, you have a beautiful theorem that is called a representer theorem that will tell you that the solution of this minimization problem can be described as a finite sum of the kernel function evaluated at your training point weighted by some coefficient alpha. But you see that this is a finite sum and you have at most n terms in this sum where n is the number of training sample. So we can recast this problem into a finite dimensional problem, n-dimensional problem. This is what's done here on this slide. So I parameterize the problem now with this coefficient alpha. I can solve the problem on alpha, and I have an explicit solution for alpha. So my final predictor, my final kernel predictor, is this guy. Okay, it's just the coefficient alpha combined with the kernel function evaluated at the training point. So it's nice because we do not need to compute the lifting of your training sample, and we can always, well, if n is reasonable, you can always compute this, right? I need a last few things about kernel methods to characterize the speed of convergence of kernel methods. You need to know the covariance operator, the integral operator, which is defined this way. Okay, so this is the integral of the kernel over the function f with respect to the distribution of your input data. So you have two types of information in this integral operator. You have the kernel that you are using and that define your RKHS and the distribution of your data. Once you know your integral operator, if you manage to study its spectrum, and in particular the spectrum of the integral operator against its resolvent, then you obtain what we call the effective dimension. And once you have the effective dimension, it will give you the speed of convergence of your estimator towards f star, your regression function. Okay? So let's go. Here, if we go back to our physics-informed machine learning problem, we have a Sobolev norm and a PDE norm. And we can show that there exists an operator, such ON here, ON, such that I can rewrite the addition of the sum of the Sobolev norm plus the PDE norm as a single L2 norm squared involving this operator. So this is nice This is very abstract, but this is nice because this will suggest some Hilbertian product, some scalar product, okay, given by this abstract operator On. And this is what's written here. If you take the Sobolev space of order S equipped with this inner product involving here the operator On that I just introduced before, we can show that this is indeed a reproducing kernel Hilbert space such that the RKHS norm matches the sum of the Sobolev norm plus the PDE norm. And the associated kernel to this RKHS is given by this here, where we have the eigenvalues and the eigenfunction here of our operator On. Okay. So I have this abstract operator, but let's assume that I know how to characterize it. If I know how to characterize the eigenvalue and the eigenfunction, then I have access to the kernel of my physics-informed problem. Okay, so good news, this is a kernel method. Next question, how do you characterize the kernel? Well, the bad news is that you have to solve a weak formulation. And as a statisticians, we are not super happy about this, but well, we give it to the world. You can compute this weak formulation and this will completely characterize the kernel. So just to give you an idea of what's happening here, I will take a toy example. So I use a one-dimensional use case, okay? So I have a segment minus LL. I periodize my function over an extended domain. So this is just for technicalities. I assume that my target function f star belongs to H1 and that the differential operator is just U prime equals 0. What does it mean? It means that f star should be approximately constant. Okay. And let's say that we are minimizing the training empirical risk penalized by the Sobolev norm and the PDE norm. Well, PDE is just an ODE here. Okay, U prime equals 0. We made the computation for you of this kernel, okay, and I put it very in a tiny, tiny font so that you cannot read it. So we can indeed compute explicitly the kernel, and if you do this, you can compute also the effective dimension by characterizing the spectral information of the integral operator, and obtain such a theorem about the speed of convergence of our kernel estimator. So what do we have? We have that our kernel estimator will converge towards f star with such a speed that is decomposed into two parts. Okay, the first part that scale as n minus 2/3, and the second part that scale as n minus 1. What is this n minus 2/3? N minus 2/3 is the Sobolev minimax rate that you can expect when you estimate just a Sobolev function. So what does it mean? It means that when this term is not equal to 0, well, overall, this bound scale as n minus 2/3. So you retrieve the minimax Sobolev rate. But if f star is exactly a solution to your ODE, so it means that this term disappears and you are left only with the parametric rate 1 over n. And this is good news because you are just estimating a constant, okay? So you used a bazooka, that is our kernel method, but you retrieve nice property of parametric learning here, where the speed of convergence is just 1 over n. So this is answering the question that there is a benefit to use the physical information into your learning procedure because it will speed up your estimation process if f star is exactly satisfying the PDE. Okay? Okay. Is it the end of the story? No, because we would like to unroll the whole kernel machinery to obtain like new algorithm. And if we always have to compute explicitly the kernel, well, this is quite tedious, right? So we do not want to have such a complicated things to implement. So the idea is to introduce what we call the physics-informed kernel learning algorithm. And again, since I'm running out of time, I will be very quick on this. But the idea is quite simple, okay? So as I said, since we are facing a kernel estimator, we need to compute the kernel. First solution that we want to use is to adopt like a finite element methods to solve your weak PDE, your weak formulation to characterize your kernel. We do not want to do this. We want to do things simple. What we are doing instead is to use Fourier series. So we will restrict just the minimization of our empirical risk penalized by Sobolev and the PDE norm over the linear span of the first element of the Fourier basis. Okay, so you do like a truncation of your Fourier basis. You choose the first elements. And we call the PIKL estimator to be the minimizer of this empirical risk over the first Fourier atoms. Okay. Is it easy to implement? Yes. So this slide is ugly, but this is easy to implement because the nice thing about the RKHS norm, so the Sobolev norm plus the PDE norm, is that you can rewrite it as a bilinear form over the Fourier coefficient of your function. Where here you have a matrix M that we can construct explicitly. I have written again the expression here in tiny so that you don't look too much there, but we can completely rewrite this RKHS norm squared as a bilinear form of the Fourier coefficient of our function involving this matrix that we know how to construct. And so that's it. Once you have this, once you have said this, you can compute exactly your PIKL estimator either by using a primal solution or a dual solution. So in the primal solution, you will recognize here, well, just the Fourier transform, if you want, for the Fourier matrix phi. And Km will be the kernel matrix, where here you compute the kernel evaluated between pairwise xi, xj, your training sample. Okay, so you have two different types, two different ways to compute your PIKL estimator. Everything is explicit. And in the first case, well, you have to invert a matrix that is n by n. In the second case, you have to invert a matrix that is 2m plus 1 to the d times 2m plus 1 to the d, where m is the number of Fourier modes that you keep in your expansion, in your Fourier expansion. So we have a slight preference for this one because this one can be computed in online fashion and in parallel. And we have actually like 2 or 3 days ago provided a GPU compatible version of this PIKL estimator that now can handle like a lot high dimension and a lot of different and a lot of training sample. Okay, so let me conclude on this PIKL estimator. We can just first check that it has nice behavior over some experiment, numerical experiment. So here in this simple case, we are looking at this PDE, well, this ODE, we are in the one-dimensional case, which corresponds to the harmonic oscillator problem. We know exactly how to describe the solution of such a PDE. This is a combination of two functions, f1 and f2, and we just compare the PIKL estimator to an oracle d-square estimator that will only fit the weights over F1 and F2, okay? So first, good news, our PIKL estimator is as good as the Oracle least square estimator that is made to only explore the space of the PDE solution, whereas the PIKL estimator is not made to do so. Okay, next, we are doing imperfect modeling situation here. So let's say that you want to solve the heat equation, or you want to estimate F star, that is the solution to the heat equation plus something else. This something else is not too large, meaning that we are not making a huge modeling error here. And what we can show is the following. So this is the most beautiful plot of the presentation, so I need to to zoom in. What we can show is that the PIKL estimator is in blue, and we compare it with the Sobolev estimator, where we remove any PDE information, and with the PDE estimator in pink, where we remove the Sobolev part. And what do we see? We see that the PDE estimator is going down, and then it's stuck. It's stuck because, well, he's made to estimate a solution of the PDE. So he cannot find something else into F star. So it will saturate the error here, no matter how large is your training sample. So the Sobolev estimator struggle a bit in the beginning when there are a few data, but then when you increase the data, well, he managed to estimate very well F star. And you can see that the PIKL estimator has the best of both worlds. So when the data is scarce, well, the PIKL will rely on the physics information and has like nice error, estimation error. And when the data is growing, then he uses it to estimate the part in top of the PDE solution, okay? Okay. Yes. So we also compare PIKL with pins, but I will go very quick over this. So here you see that we have a pin, we have a PIKL, and obviously this is the function that we wanted to estimate. So, you can just look at the picture. And not to be provocative, we also just compare the PIKL with some PDE solvers. And of course, PDE solvers are super efficient to solve PDEs. They are designed for that. So traditional PDE solvers outperform the PIKL estimator, of course, for some PDE. So here, this is the case for the wave equations. But the PIKL estimator may be nice if you try to solve a PDE that contains some noisy boundary condition. Here we see that the traditional PDE solvers can struggle with noise in the boundary condition. The PIKL estimator remains a robust alternative to solve your PDE, while requiring a few data points with respect to pin implementation. Okay, so I'm sorry to have been so long. Here you have all the paper that I talked about during the presentation, the pin paper, the kernel paper, the PIKL paper, and the last and new one, which is a GPU compatible implementation of the PIKL algorithm, where you can also find nice GPU implementation for other types of prediction problems involving time series or kernel methods. But I won't say more about it. I really thank you for your attention.
Thanks a lot. Thanks for an absolutely fabulous talk. Let me see, are you still looking potentially for a postdoc for this fall, or that been?
So I should have hired someone, but I may have some other funding comings, but I'm waiting for some answer.
I see. Okay. Well, if anyone's interested, there's something on your webpage still. You can
Yeah.
check out job ads if you want to get pickled, so to speak. I'll end the recording here and then let people ask any questions they might have, unmute, use the chat, however you want to go ahead and do so. Thanks again.